Okay, you can get started.
So
feel free to chat me, Megan, if you have any technical needs.
okay, cool. So I hope our Francophone audience join the French room. So now we're gonna get started. Give me 1 second and I will pull switch to my screen here. Can you guys see my screen?
Yeah.
Great. So again, today we're gonna hopefully be doing 3 chapters. The first one being what is programming, where we are going to talk in a general way about computer programming and software programming specifically. And when we get that done, we're gonna move on to math prerequisite, which are some fundamental notions in mathematics that needs to be, kind of mastered in order to ease Haskell learning curve. And last, we will move on to applying all those concepts in math to Haskell. So we'll do a little bit of coding and see how all those notions that we learn in mathematics apply to Haskell. So what is programming? Programming is simply a process that allows us to, or through which we create a series of instructions that then tell a computer on how to perform a task. I really love these simple definitions because very often we get into too many complicated definitions, but at the base, it's really about creating a series of instructions that will allow a computer to, or tell a computer how to perform a task. What are instructions? Instructions are just, something you write in a programming language that can then be translated into another thing that the computer can understand. So then we move on to the notion of a programming language. A programming language is really just a language that allows humans to interact with the computer. So we mentioned that you need to give instruction to the computer to perform a task, and those instructions are simply written using a programming language, Haskell being one example of a programming language. So the computer at its level doesn't understand that language right away, but it has the tools to grind that language down to something that it understands, and we'll see that later. So we write those instructions in something, and usually we write them in a file that we call source code. So the instructions that we write within the file to give to the computer to work with, we call them source code. And the source code is written in the file, which is at its turn called source file. So we have a programming language that allows us to write instructions that we can write into a file. And once we write them into a file, we call them source code. And the file itself is called a source file. And next, what happens is that we take that file containing a source code and we pass it through a process that we call compilation. So compilation is really about getting that source file and getting the language or instructions that we wrote within it inside and converting it into something that the machine can actually understand. As I mentioned before, machines only understand a language called a binary language, meaning they all only know about 0 and 1s. So when we write our source code, our instructions using a programming language, for the machine to understand that language, it needs to transform it or to compile it into something called binary. I see that someone is having fun with the slide here. But yeah, so then once we compile that file, once we compile the source file, we end up with something that the machine, we end up with a binary file that the machine can actually execute. And executing that binary file would, result in the machine performing the tasks that were specified within the file. So to give you like the big picture, we start with a programming language, which is the way to communicate to the machine, but it's high level enough in such a way that we can understand what it means. Us as humans, we can understand programming languages, but the machine at its level only understands binaries, which are 1s and 0s. So we go through a process called, we create a source code, which are instructions that we write in the source file. And then we take that source file, we pass it down through a process that we call compilation. And, what we get at the other end of the process is a binary file, which can then go through another process, which is called execution. And this time, it will actually perform the tasks that were written inside of the file. So that's the process. That's what programming. That's how we can define programming in a general way. Are there any questions at this point? Great, I will take that as a no and we'll progress. So next, the notion we want to talk about is programming paradigms. And paradigms are actually how you see or how you perceive reality around you. Paradigm is about the tools that you use to understand, your entourage, meaning your surroundings. Let me step a little bit away from programming in the sense of computer and talk about the word paradigm, because this word tend to cause a little bit of issues, some issues. A paradigm, if we here in Cameroon and in Africa in general, for example, when a baby is born, we might have some rituals that we perform. That means something in our context, the local context. If you go to Asia, it's a totally different thing. you know, and that's a paradigm. So that's the way we understand the world around us, or the way we picture things or analyze things around us. So we have the same concept in programming, and the main paradigms that we have are, the imperative paradigm, the object-oriented paradigm, and the declarative paradigm. And they all differs on how, they have different approaches to designing software or translating the reality around us into software. Because at the end of the day, when you're programming, you are not programming out of thin air. You are taking a situation that you're going through, and you are trying to translate it into software, into code. So in declarative paradigm, they tend to use to be more declarative, in the sense that they state what the program needs to do, and they tend to they tend to not say how to do it. That's the declarative paradigm. So a life specific example that I hope we all know, could be driving a manual stick shift car and driving an automatic stick shift car. When you are in a manual car, you get to a hill, you will actually tell the car what to do by switching gears. You go from, let's say, the fifth gear, to the fourth, to the third. As the hill gets serious, you have to. So you're actually telling the car how to do it step by step. So you're specifying the instruction and telling the car how to do it step by step. As opposed to an automatic car, where you actually just state your intent. As you look up the hill and you say, I want to get there, you're actually telling the car what you want and not how to do it. So the car will figure out how to switch the speed on its own, as it becomes necessary. So that would be an exact specific example of an imperative programming paradigm and a declarative programming paradigm. So just to resume on these two, imperative is the how, telling you how to do it. Declarative is the what. I'm expressing what I want. I know you know how to do it, figure it out by yourself, but this is the result that I need. So that was for those two, imperative and declarative programming paradigms. Now, the object-oriented paradigm which is mainstream, I would say, actually falls a little bit under the imperative paradigm. But the difference is that with object-oriented paradigm, you see the world, or you see your reality around you through classes and objects or components very often. When it comes down to declarative programming paradigm, you see the world around you through functions. So everything is function, or everything is logic, if I can put it that way. And in the case of Haskell, Haskell is a functional programming paradigm which uses function. Functions can be used to do pretty much everything in Haskell. Java would be an example of object-oriented paradigm, and the tools that Java use are classes and objects. So as we said, paradigm is how you interpret your reality around you, the tools you use to interpret your realities around you. So are there any questions so far? I'll take that as a no and we'll progress. So here we have some examples. I think I already highlighted that one. Java is actually an object-oriented paradigm. We do have C++, which integrates two paradigms, object-oriented and procedural. Down here we have Haskell, which is what we are mostly interested in. It's functional oriented. And lastly, I want to mention maybe these two, F# as a functional programming language, although F# does include or allow you to perform, object-oriented paradigm. It's mostly functional programming oriented. JavaScript, finally, which I would say it's a little bit of functional programming and procedural, maybe a little bit of object-oriented, but just to say, it's not always like a clear frontier as some of these languages are trying to incorporate, notions from other paradigms. Are there any questions? No. So we'll move on to mathematics. So just as a summary, what we're trying to achieve here is to give you elements of set. I mean, it's to give you the tools to understand a little bit about the set theory, and also giving you the tools to understand a little bit about functions in mathematics. Let's get started here. So what is a set in mathematics? A set is simply a collection of pairwise distinct objects that we call elements of the set. So as an example, we here are the participants of this specific hackathon form a set. We can think about all the computers that the participants are using or will be using throughout this event can form another set. So it's as simple as that. The only rule which is essential is that the elements have to be pairwise distinct, which simply means that I'm not going to have, let's say, two mouthfuls in the set of the participant of this hackathon. Otherwise, that would be the same mouthful. So if I take mouthful and I start checking other member or other element of the set of the participants of this hackathon, I'm not going to find any other person which is mouthful. If I were to do, that will be mouthful. So there are two ways that we can define sets in mathematics. We can define them using the extension form, which actually gives all the elements of that set in an explicit way, which means if I go back to our example of us at this hackathon, June 2022, we form a set that we can express in an extension form. So we just line up and say Manfo is the first element in the set, Megan is the second, Kala is the third, and so on. So we'll list explicitly all the elements of that set. The other way to define a set is using comprehension notation. And in this case, what you do is you figure out a property that all the elements of the set respect. What is a property? A property is just, let's put it simple. It's, I would say, a sentence that you can say whether it's true or false. So if we take the example of the participant of this set, I would say that out of all the people on Earth, the elements or the participant of this set are those who register to the event, who click on this specific link, invitation link, Zoom link, and who are here watching me, so that's my property. And I can pick someone who is in here and say, did he register to the event? I would say probably yes. Did he click on the link to join? Yes. Is he watching me at this specific moment? Yes. So that's a property that defines all the elements of the set. And as you can see, not everybody is going to fall into that property. If we pick someone who is walking out there on the street now, and we try to see if he adheres or verify that property, the answer will probably be false. So here as an example, we can consider the set E, the set of even integers between 0 and 10. Even meaning they are divisible by 2. And then the elements of the set would then be 0, 2, 4, 6, 8, and 10 himself, because those are the elements between 0 and 10 that are divisible by 2. So here our property is that the elements are between 0 and 10. In addition to that, they are divisible by 2. So that is an example of a set that we can write in extension. As you can see, we are specifying there all the elements of the set. Or we can write in comprehension, which is just saying that for all elements x that belongs to natural number being like those 1, 2, 3, minus 1, minus, and so on. If we consider that there is a k, another number belonging to n, and then we can say x equal to k, because for a number to be divisible by 2, it has to be a multiple of 2. So, and that's one property. So our number should be defined like that, in such a way that they are multiple of 2, or n. This is meaning that, we are adding another property. That symbol there is n. The element we are considering should be within 0 and 10, or between 0 and 10. This is just to mean that, it's all the values within this interval, 0 and 10, inferior or equal, inferior or equal. So are there any questions about the definition of a set, the 2 ways we can do it? I would say no. So let's progress. So just some notes here. As I said, a set comes with elements. And given one element, you can say whether it belongs or not to a set. And in mathematics, the way you write it is using this notation. So if we have a set A that we call A, and then we can pick an element X, X could be anything, and we ask ourselves, does X belong to the set A? So that would be the notation. That's a little bit like an E that you cross, I don't know, but that's how you would write it. well, this is actually not belonging. So X does not belong to A, and over here, X belong to the set A. I think this is pretty self-explanatory. So as an example, if we have E, our set equals those numbers, and we can clearly say that 4 belongs to E, or we can state that 5 does not belong to E because 5 is not part of the elements of this set simply. So there exists one set. It's the set to which all elements belong. You know, mathematicians are kind of crazy with this notation. They create notations all the time. So I think it's called omega. Omega, and is what we call set universe. And all elements belong to that set. So no matter where you get the element, it belongs to this set. Now, we can start talking about like some characteristic of sets. Sets can be empty. Empty just means that the set doesn't have any elements. You know, I can define a set of all people, let's say, who are connected to Zoom, to this specific link, but do not have a computer device. By computer, I mean it in general sense. I think that would be an empty set, for example. An empty set, we could go into a classroom and state a sentence like, we want all the students that have obtained 0 in a specific subject. And if we are in a classroom where no one obtained 0 for that specific subject, and then we'll be talking about an empty set because there's no student that actually meets that condition or that property. So in mathematics, the way you write empty set is that 0 that you then cut with a bar like that. That's called empty set. So now if we move on to set cardinality. Set cardinality is actually a way to count the elements that you have within your set. So again, if we go back to our example of all the participants of this hackathon, you know, I can give it a cardinality. Its cardinality would simply be how many people are actually distinct. I want to highlight that actually attending this hackathon. So if we go back up here with our set, you know, we can simply state that the cardinality of E is 6 because we have within 6 here, within the definition of E, we have 6 elements that are distinct. You know, in case we had, let's say, another 8 in here, we would count it as 1. So it doesn't matter how many duplicates we have, we'll count them as 1. And that sends us back to the definition of a set being a collection of pairwise distinct elements. So, and the way you note cardinality in math is using this card between parentheses, your set. So, yeah. Are there any questions on empty sets and set cardinality? Is it pretty clear so far? I would say yes. So now let's move on to subsets. So, we say if we have two sets, A and B, and we say A is a subset of B, if all the elements that are in A are also elements of B. So let me take one example to get it clear, get it across. We have all the participants to this hackathon. That's our set. Within this group, we have brave women, we have brave men, and those two form subsets of the parent set, which is participant of the June 2022 hackathon. So one subset could be the group of brave women that are in the hackathon. And another subset could be the group of brave men that made it to this hackathon. So those would be subsets. So you can clearly see that the group of women belong to the big group, which is the participants of this hackathon. Likewise, the group of men belongs to the big group of the participants, which is the participant, or the big set, which is the participants of to this hackathon. So a mathematical way of saying that is that no matter which element, if we take any element we take in such a way that that element belongs to A, then that element also belongs to B, which is exactly what we said. We said, if A is a subset of B, it means all the elements of A belong to B. And we also note it in this way. So we say A is included in B. So that's the symbol, and we read A is included in B. So some example down here. So if we have the set of these elements, we have 0, 1, 2, 3. Well, a subset of that set could be 0, 1, 2. It could be 0 on its own. It could be 0 and 1 as well. So, and we use this notation to say this set here is included in that other set. And this other set on his turn is included in a bigger set of natural number. And we can go like that till we get to R, and which is a set of all the real numbers, and C, which is a set of all complex numbers. So yeah. So, and as you can guess, we talked about empty sets, and naturally empty sets would belong to any sets out there. So empty set doesn't have any element. And if you get a set that has element, I mean, it was an empty set before it became like a set with elements. So that's just a property or something that is like, it's called pretty much like an axiom in math. So naturally, the set A is included in itself, because when we get this set, we can say 0, is a subset of this set. 1 is another subset, 2, 3, and so on. Now we take them 2 at a time, 0 and 2, 0 and 2, and 1, 0 and 2, 0 and 3, and so on. So just let me share my screen very quick so that I can detail this example more. So I'm gonna switch here. Give me 1 second. I'm gonna pull up my screen. Can you guys see my screen?
Yeah.
Awesome.
Yes,
So just as an example, we are talking about this set. So we have the set that has those elements. And 1 second here, let me fix that. And we are trying to figure out like its subsets. So a set containing the element 0 is definitely a subset for our starting set. All the elements within this set, which is only 0, belong to this set. So that's the definition of a subset. If we take the second one and we give it, let's say, these 2 elements, we can clearly see that this set is still included in our starting set, which is 0, 1, and 2. Bear with me here. So clearly, 0 and 1 are also elements of this set, whose elements are 0, 1, and 2. So now, if we continue, we have 0, 1, and 2. Well, it's itself, so it's clearly included in our starting set. So in this case, we have the property that I just showed you, which is any set A is actually included in himself, or is a set of himself itself. And to end, so if we just write that, which stands for empty set. The property is that empty set belongs to any set out there. So I can clearly say that empty set belongs to, 1, 2, 3, 0 there. Bear with me. So 1, 2. I can also say that empty set belongs to, I'm just going to say all participants. I'm going to continue down here. Participants to the June Hackathon. So empty set belongs to all the sets with no exception. Are there any questions so far? Okay, so I'm going to switch my screen. Bear with me 1 second. Okay, can you see my screen? My other screen? Great. So now let's move on to set equality. When we have two sets, A and B, we can, legitimately ask whether they are equal or not. And it's very simple. Two sets, A and B, are equal only and only if they have the same elements. So, if we then use the included construct that we use to define subsets, this meaning A is included in B, or A is a subset of B. Now, if A and B are equal, it simply means that A is included in B and B is included in A. That's what it means. So as an example, if we have this set with 0, 2, 4, 6, 8, and 10, and then that's set E, and then we have another set F, which is 6, 8, 10, 0, 2, 4, 6, 8. We definitely have equality here. And remember, duplicates don't matter. So over here, it's as if we had, 6, 8, just 1 8. We have 2 there. Then 10, then 0, 2, 4. And we omit this 6 because we already counted 6. So they have the same element. So let's go back to the set of subset this time. So I think I'm gonna switch my screen again to explain this. Give me 1 second. Just 1 second here. Switch my screen. Let me erase that. So now we're talking about set of subsets. So as a starting point, let's say we have a set defined like that. Next, let me just remove one element to make it a little bit easier to get the notion across. So we have our set that we define like that. And then we can ask ourselves, what is the set of its subsets. So we want to figure out the set of all the subsets that we can have there. So our first step is to define all the subsets that we can have here. And if you remember, the empty set actually belongs to all sets. So that's the first subset of this set. Then we can pick the elements one at a time. So we have the set 0. I mean the set with the element 0. We have the set with the element 1. And then we have the set with the element 2. But we can't stop there because, you know, we can combine them 2 at a time. We have 0 and 1. And we can also have 0 and 2. It still doesn't end there. We can have 1 and 2 as well. 1 and 2. So these are all subsets of this set. And we can create another set, a new set, which elements are these guys. So if we call it P, we'll call it P. If we, let's just digress a little bit and call this set E. So call it P of E is equal to, you know, I will just open and copy all of this, put it in there and close it. So I can do this. So that's the set of all the subset of E. So that's the definition. And clearly, if I switch back to my other screen, to stop sharing here. Share here. So if I switch back to my other screen, then I hope it makes sense now. So if we have A as a set, and then the set that we call P, parts of A, that we can call P of A, is the set of subsets of A. So, and then we have these properties, which is the empty set always belongs to the part of a given set, because empty set is included in, you know, in A. So we also have that a set A always belongs to the set part of A, because A is included in A, you know, and I think when I showed you on the other screen, I didn't include A in our case was E, you know, like a set always belong or is included within itself, if that makes sense. We will detail more when we get to the practice session tomorrow. So are there any questions here? Okay, I'll take that as a no, and we will progress. So now we can run some operations on sets, you know. The first one being intersection. And really intersection is just about figuring out, you know, the things that belong to both sets at the same time. If we go back to our set of, let's say, the participants of this hackathon. And then we think about the participants of the previous hackathon. So we already have 2 sets there. And we ask ourselves, what's the intersection between those 2 sets? So on one hand, we have participants from the January 2022 hackathon. Let's say we have Richmond, we have Pamela, and then we have Megan. On the other hand, we have participants of this hackathon. Let's say we have Fotio, we have Pamela, and then we have Didier. Clearly, we can tell that Pamela is within the intersection of those 2 sets, because Pamela is a participant was a participant to the January 2022 hackathon, and she is also the participant to the June 2022 hackathon. Oh, I wish you were actually there, Pamela. This is, that's the intersection. That's the definition of what an intersection is. So in the mathematical sense, you know, intersection, that is noted like this, you know, with that, you can say upside down U is about figuring out all the elements that belong to both sets at the same time. And it reads A inter B, or the intersection of A and B. So that's how you would read it. But notice something interesting here is that we can then reuse this intersection notion with the notion of a subset. And we can say that, you know, if we have 2 sets, A and B, and we figure out something that belongs to both of them, that thing is definitely a subset of A. Well, clearly, if it belongs to A and B, it belongs to A, it belongs to B. So if something belongs to B, to A, you know, it clearly, I mean, is a subset of A. And same here. So as an example, if we have our set, our starting set, where we have those elements 0, 2, 4, 6, 8, 10, and then over here we have our set F with this element 3, 10, 2, 8, 8, 5. We can infer or conclude that E inter F is actually equal to 2, because 2 both appear here and here. 8 does appear here and here. And remember, duplicates, we don't really care about it. And then 10 appears both in the set E and in the set F. So that would be another example. Are there any questions on the notion of intersection? I would say no, so we'll move forward. So now next we talk about the union. The union is, you know, that's how it's noted. When we have 2 sets, the union is actually just the sum of all the elements, you know. If it reads A union B, or the union of A and B. So that's how you would read this. And clearly, if we consider this example, we see that, you know, here are the elements of E. Over here, we have the elements of F. So the intersection is actually all the elements. And again, remember, we don't care about like those duplicates. So we just take one of them. So that's the union. So the union is like added. The intersection is like, what do we have in common? And then we move next to a very important notion, which is how we figure out like the cardinality of the union of two sets. And remember, the cardinality of a set is just how can I say it? The cardinality of a set is simply the number of elements that are within the set. So we count them, and that number represents the cardinality. So now we've got this formula which says that if I have a set that is a union of A and B, and I want to calculate its cardinality, it's actually you know, cardinality of A plus cardinality of B minus cardinality of A intersection B. So in a sense, if we go back to our example of participant to the previous hackathon and participant to the current hackathon, if we have you know, an intersection that is not an empty set between those two sets, and then if we ask the cardinality of the previous participant, the participant to the January hackathon union, the participant to the June hackathon, we would use this formula to figure it out. We would on one side figure out the number of people we had on the January hackathon, and then figure out the number of people we had on the February hackathon, and remove from them all the people that appeared in both hackathons. That's how we'll figure out like how many people we have. Are there any questions so far? Wow, great. Okay, so next we will move on to some properties. So properties in mathematics are, you know, statements, I can call it like this at this point, that are true, you know, or that always verify, that are always true. So the idempotence property states that if I have a set A and I try to calculate its intersection with itself, then I will obtain A. Because remember, intersection of A and A, I'm trying to figure out the elements that are in A and that are in A at the same time. Well, clearly, it's all the elements, so A. Commutativity. Commutativity just means that, you know, in respect to this operator here, which is the intersection operator, I can commute. Like I can commute. So I start with A inter B, or the intersection of A and B equals the intersection of B and A. That doesn't change anything. So you say this operator here is commutative. So that's the property of commutativity. Associativity is saying that if I have 3 sets and I'm trying to figure out the intersection, I can group the first 2 and figure out the intersection, and whatever result I get from it, I will try to figure out the intersection of that result with the remaining set, the 3rd set. I will obtain the same result if I did it the other way. If I started with figuring out the intersection between the last two sets, B and C, obtaining a result, and then trying to figure out the result of the intersection of that result with A. So that's the associativity property. And we see this with addition. So when you have, like, let's say 1 plus 2 plus 3, you can start by adding 2 to 3, then you get 5, and then you add 1 to 5, you get 6. Or when you have, you can go the other way. You can have, you have 1 plus 2 plus 3. You start by adding 1 to 2. The result you get, you then add it to 3. You will still get 6. So you say the addition is commutative. And then we have other properties, which is the neutral elements. Remember we talked about the universal set that we call omega, the set of everything. So if I have the set of everything and I have a set A, I try to figure out like the intersection between my set A and the set of everything. I know that in the set of everything exists my set A. So when I do the intersection, I will get A. I will get A. I hope this one makes sense. So that's the property, that's a neutral element property. So these properties are for intersection. And we have similar properties for the union operator. So if I have a set A, a union, a set A, well, I will end up with duplicate that I can easily remove. So I will go back to the set A. That's idempotence, meaning it doesn't change. Idempotence means it doesn't change. Commutativity. If I have a set A that I put in union with a set B, I can also obtain the same result by doing the set B union the set A. So the union operator is commutative. So if we move on to the associativity, it's the same thing with union. So if I have 3 sets to put in union, I can start with associating, with the last 2, get the result and perform its union with third set, just as it shows there. And the union also has a neutral element. Remember the neutral element for the intersection was omega, the universal set, the set of all the sets. Now with union, we have A. If we have A, we put it in union with the empty set. We know the empty set doesn't have any element, so nothing will be added to the set A. Well, the set A have. So if we have, let me step back. So if we have A in union with the empty set, we're not going to get any additional element in the empty set. We saw that it doesn't have any element. That would be the same as saying empty set union A, and this would be the commutativity property, and that will still be equal to A. So many more properties here. This one is distributivity, which means that if we have B inter C and then we try to do the union with A over here, we can expand it to this form. So we can do A union B, inter A union C. So just to let me share my screen and explain this with addition and multiplication. So share my screen. Bear with me a few seconds there. So give me 1 second. So, so what we're saying here is that A, well, let me first write what it is. This TDT property. Okay, so if we have a set A that we try to union with a set B that is an intersection with C, we say it's equal to A union B inter A union C, A union C. So this is simply the distributivity property that we see in addition and multiplication. So if we have, let's say, 2 that we want to multiply by 4 added to 3. So this is simply equal to, we take 2, we multiply by 4, 2 times 4, and then we add the plus there, 2 times 3. So we say that multiplication is distributed over addition. So because we started with addition, but we're able to distribute that operator, which is multiplication. So which is the same over here. So union is, I forgot the term, but I think it's distributed over intersection. So are there any questions here? I would say no, so I'm going to switch back to, if I can figure it out. 1 second, bear with me. Give me 1 second. So we're going to switch back to this, and you know, the same thing is true for intersection. So when we have intersection here and union there, you know, this is how we can define that operation. So difference, this is how we note the difference. So we have set A, set B, and we are trying to figure out like what's the difference. Simply means that we are trying to capture all the elements that are in A, but not in B. So we are removing all the elements, the B elements that duplicate in A somehow. So the symmetrical difference noted like this, you know, we have set A and B, and we are interested in elements that belongs to A union B, but not to A intersection B or inter B. You know, we can also use this formula here to calculate it, which is refers to the difference. So the symmetric difference of two sets is actually about calculating the union first and then removing all the element within the intersection. So next, complementary. Complementary, as the name kind of gives us a hint. If we have set A, its complementary is everything that belongs to the universal set. But at this point, what we do is we remove all the elements of A in the universal sets. So it's as if, let's say we are in a house and we have like the set of all the keys. If we consider like one set that only have, let's say, one key, then its complementary is all the keys that are in the house except for that key on its own. So that's the notion of complementary. Since here the universal set or universal set is actually everything else that holds like all the possible sets, we use it to define the notion of complementary, because we just need to go into that universal set and remove our set, and all the thing remaining will be the complementary of our set. It's clear that if we go forward and backward with this notion, I mean, that's how complementary is noted. But if we do complementary 2 times, it brings us back to where we were. So with the example of the house, if we let's say in a house have kids, and we take one kid and we question ourselves, what is his we take one kid as a set, what is his complementary? It's all the other kids, they form the sets. It's all the other kids. Now if we ask what is the complementary of all the other kids, it's everything except for himself. So within the house, the context of the house, we will go back to that other kid, if that makes sense. And here we have the Morgan law, which just says that the complementary of the intersection of sets equals to the complementary of A union the complementary of B. And the complementary of the union is equal to the complementary of A inter the complementary of B. So these are things that I hope we will be able to get through when we do the exercise session tomorrow. So next, the Cartesian product. The Cartesian product of 2 sets, A and B, that we note, A times B cross B, is defined as follows. So we have there, curly braces that we use to introduce a set. And now we give it a property. And remember, since we're giving the property, here we call it a definition in comprehension. We can't possibly list all the elements that belong to the Cartesian product of A and B, and we'll see why later. But here, the way you define it is all the couple of elements where A, this A here, and that couple belongs to A, and there's a tiny mistake there, that's French, and B belongs to B. So all the couples that we can make, drawing, okay, elements from A and B in this fashion, where A belongs to set A and B belongs to set B, are called a Cartesian product of A and B. Okay. So one specific example could be the brave women of this hackathon forming a set. The brave men of this hackathon forming a set, and we are interested in forming a group for the challenge exercise and want to bring in some equilibrium. So we say, okay, we're gonna form like couples with, a woman and a man. So you see, we'll have to go into the group of women and pick one woman, and go into the group of the set of men and pick a man, and form like a couple for the group challenge. So that will be an example of the Cartesian product. And this notion doesn't just stop to two sets. You can have an infinite number of sets, just like you see here. You can have an infinite number of sets, A1, A2, A3, K being a number. And you can figure out the Cartesian product. And the formula is simply, making this couple. I don't know if I'm gonna call it couple now, or tuple. There you go, where you have like respectively A1 element belonging to A1 set A1, A2 belonging to set A2, and AK belonging to set AK. So the Cartesian product doesn't stop to two sets. So as an example, we have the in computer science, when you the colors we see on our screen, like this red or whatever, this white, all of this comes from a triplet where you have red, green, and blue, and you mix them up to get like a specific color. So the red, you have to pick it from this interval from 0 to 200, and that's all the elements of the set red. You can also, it's the same thing for the set green, and it's the same thing for the set the blue set. Okay. So I think we might want to take a break if Megan can confirm. And then when we come back, we will move on with the functions. Is that right? Are there any questions before we take a 10-minute break? Okay, I would say no. So feel free to grab a cup of coffee or whatever, a glass of water, and we'll be back here in 10 minutes, which is on my clock, 1:55 UTC +1. So I will see you then. Hello, everyone. I hope you're all back here. So we're going to proceed with the functions in math. So definition. So if we consider we have two sets, A and B, that are not empty, and I hope by now we understand what a set is and the fact that they're not empty, you know, we consider a relation that goes from A to B, meaning a relation that is able to, you know, pick elements from A and transform them into element in B. So the relation R is called a function if any element that we pick from A is related to at most one element Y that we pick in B. So I'm going to repeat that, very important. We have the concept of relations. So you have a departing set and an ending set. The relation links elements from the departing set A to elements in the ending set B. That relation is called a function only if any elements that you take in A is related to at most one element in B, which means if I take an element in A and it relates to more than one element in B, that is not a function. It's simply a relation. It becomes a function when we have exactly one or none. Okay, so you know, again, as mathematician, love this notation. So you can see there that any element we pick in A and any element in B, you know, if we consider another element in B and we say that X that we pick from A is in relation with Y that we pick from B, and X is in relation with Z, that would mean that Y equals Z. So I'm picking one element from the departing set, and I'm saying that I have two elements in the ending set in such a way that my element that I picked from the departing set is in relation with the first element in the empty set, and it's also in relation with the second element in the empty set. In that case, those two elements are the same in the ending set. So that's the definition of what a function is. In real life, a function would be, if we go back to those who participated, you know, we could think of a function that takes one participant in this our starting set and then return his name. You know, you see that one participant has at most one name. You're not going to see participant with like two full names in general. So the way, you know, if a relation is a function, then we can denote it f of x, meaning function of x, x being an element from the departing set, y being an element from the arrival set, and f being like the function, meaning the relation, the transformation. And you can write it this way. So it reads, f is a function that goes from A to B that associate at any x belonging to A, f of x. So that's how it's you read it. So as an example, you know, if we consider, let's say, we have real numbers, which are numbers that can come with like decimal parts. And then we are trying to take a real number and figure out like its integer, like its whole part. Like we are getting rid of the decimal part. Decimal parts meaning the parts that comes after like the comma. Then here our function could, you know, this relation is actually a function because I'm not going to get an element, a real element that has like two different decimal parts. I think by looking at the counter example, it will make more sense. So let's say we have a relation that goes from z, you know, it's the set of relative numbers, integers, to z, you know, to itself. So the departing set is equal to the ending set, which to any relative integer x associate the relative integer y in such a way that x is the square of y. So here you can clearly see that 4, if we pick 4 in the beginning set, let me share my screen with share my other screen to explain this very important notion. So bear with me 1 second there. So we have a relation that we call R that is defined. 1 second. R that is defined from Z to Z, and which at any x, we have x and y. Y, we are taking it from this set. X, we are taking it from there. This is the starting set. That's the ending set. We say that our relation is that x and y are defined in such a way that y or x instead is the square of y. So which means what? The square. So if I take x equal 4, for example, I could take y equal 2. If I take x equal, let's say 16, I could take y equal 4. So clearly you can see that x here, 16, is the square, y, x is the square. Yeah, x here, 16, is the square of y4. X here, 2, is the square of y2. But now, the problem is that, you know, if we take the same x equal 4, and then we realize that y could also be equal to -2. Why? Because my relation is x is the square of y. So 4 is also the square of 2. And here we have the same 4, which is the square of, no, here I meant 4 is the square of -2. And here we have the same square, which is the same 4, which is the square of 2. So now we have x equal 4 that is associated with 2 and is also associated with -2. Our definition states that to be a function, this x might either be associated to nothing or at most to one element. So in this case, we have 2, it's associated with x 2 elements, so that makes it not a function. So let's see. I'm going to switch my screen here. Are there any question on this very important notion of definition of a function? Cool. So function range, what is the range of a function? The range of a function is simply the range of a function is just that subset of element that have an corresponding element into that. Let me put it in a different way. So a range of a function, is actually, a subset of the departing set whose elements are connected to elements in the arriving set. So A could be in such a way that some elements in here are not connected to B through the relation or the function. But when we start talking about the range of a function, we narrow this set down to only the elements that connect to at least or exactly one other element in here. So that would be the range of the function. So likewise, we can talk about the inverse range of an element y in the arrival set. So if we pick an element in the arrival set of the definition of a function, and then we can navigate back to which element from A it corresponds to. So that would be the inverse range of an element. And we noted like f minus 1 of y. So I think if we move on to some example, you can understand better. So if we have, let's say, this function here, and my bad, this is x squared. If we have this function here that takes an element x and transform it in this way, then we can calculate f of 0. So f of 0, we would come here and replace x by 0 and then add 2 to it. So in this case, we will have 0 power 2, that's 1, plus 2, that's 3. So if we f minus 1, so this is a mistake. It's actually like that. So the minus 1 is like on top there. So f minus 1 here, what we're saying is that 6 is the element in the arrival set B. And we want to figure out like the element in the departure set A in such a way that, we resolve this. So in this case, what I will do is share my screen very quick, my other screen, so that we can resolve that. One second. So we have our function f of x equal x squared plus 2. And now we ask to calculate f of 0. So what we do is we come in here, we replace x there by its value 0 in this case. So 0 power 2 plus 2, and 0 power 2 is 1 plus 2, that equals 3. So if we are asked to calculate f minus 1, which is the inverse range, f minus 1 of 6 is equal to, we want to figure what f minus 1 of 6 is equal to. So This 6 is actually representing this here, as this is how we calculate the elements in the arrival set. So the equation we will have will be x squared plus 2 equals 6. So we have x squared equals 6 minus 2. And then lastly, we'll have x square equal 4, x equal 4, which is 2. So x equal 2. And you can verify that by coming back and doing f of 2 equal 2 squared plus 2, which is equal 6, the 6. Okay. So, I will invite you to do more of this, but as of, let's look at the next one, which will allow us to introduce a new notion, which is image of f. So image of f is actually, we're no longer talking about the range, but here we are talking about like all the subset of elements in the arrival set that have, you know, a departing element in the starting set. So remember, in the starting set, we can have elements that don't have, you know, a relation in the arriving set. So the image here is all those elements that have the counterpart in the starting set. So the image of f here, I will leave that as an exercise for you, as we need to power through a little bit faster. And same for f, the inverse image of the interval 11 to 27. We just mean find the elements in the departing set A in our case that actually fall into this when they are transformed through f of x. And we'll come back to this tomorrow in more details. So I'm going to switch back to my main screen here so that we can move forward. Okay, so again, the range of a function is actually also its domain. So we can say domain or range, and this is how you note it. You write it d of f or simply df in that way. So we can do operations on functions. You know, if we have f and g, there are two functions that are both defined from A to B. You know, we can consider doing all these operations on functions. We can have f plus g defined as follows. You know, you have to make sure that the addition is defined for f to x and g to x. So f minus g function that is defined as follows, and so on. We'll see more example of this tomorrow. So function composition. So the composite of two functions is written as follows. So we start with you know, two functions, and then we want to compose them. And composing two functions just means, you know, actually when we write it like this, what we're actually doing is using the second function f as the starting set for the first function. So in order to understand this, we can visualize this. So we have, let's say, an x from the starting set A that you see there. We have an ending set B for the function f. So the function f takes elements x from A and transform them into elements in B through its definition fx x. And at the same time, we have a G function that takes its elements in B and then transform them into elements in C. So as you can see, f of x becomes like elements that G can take and transform them into this. So it's as if the x for G becomes f of x. And some example here. Let me switch back to the screen and we can do some example. So if we take, for example, these two functions, we have f of x equal x squared, and we have g of x equal 2x plus 1. Then our first question is, what is f wrong g of x? Well, it's simply as we said. So it's we know that it's equal to f of g of x. So it's as if we are replacing our x from here with g of x. So in that case, we come in here and we replace x squared by g of x. So in that case, we have 2x plus 1 squared. So that would be f wrong g. B, we have g wrong f of x. In this case, it's g of f of x. And it's as if we are coming into this function here and we are replacing x by the value of f of x. So if we do that, we will obtain, 2, and then x, we replace it by x squared. So x squared plus 1. So that would be g wrong f. And I think from here you can do the other examples as homework, and we will come back to it tomorrow. Are there any questions on function composition? Okay, so we'll move on with the function taking multiple variables. So far we've seen functions that only take one variable, x, but actually functions can take multiple variables, and one example of a function taking multiple variables would be a function that takes that couple of elements. And if you remember, this is a Cartesian product that we saw when we were talking about sets. You can see the starting sets there is R squared, which just means R times R, which is the Cartesian product. So here we have a function that takes two elements, x and y, and do this calculation on it. So that's the function with multiple parameters. I don't think we're going to spend too much time on this one. It's just knowing that whatever you get in here is what will appear over here as elements. Same here. This time elements, we have two elements and they are themselves couples or Cartesian products. And you can see that over here, we are using them to do that calculation. So parametric functions. Parametric functions are functions expressed in terms of a parameter. I would put it that way. So basically, you have a function. You have a function that depends on one parameter. And as you provide values to that parameters, you get new functions. One example here, if we take this as an example, we can say that this function is parameterized by k because, you know, as a starting point here, all we're seeing is x. K doesn't appear here in such a way that we can talk about like multiple parameters or variables for the function. We only have x there and we have a k appearing here. So for each value I give to k, I obtain a new function. So I give k1, I obtain a new function, 2, a new function, and so on. So that's parametric functions. And we will come back to this in more details when we do exercises tomorrow. So in general, you can see this notation, which goes back to the Cartesian product, where you have x and m, you know, x being like the element from the starting set A, m being the parameter of the parameterized function coming from that set m. That transform, you know, for every couple, you obtain a function in m, like we said. So you obtain a function in m. When you pick a value for m, you obtain one specific function that depends on x. And, you know, we have more notations here that you could definitely look at on your own. I think it means they're pretty much the same thing. So I know it's a lot of material to digest, and the small amount of time that we have, we need to use it efficiently. And I'm also assuming that you had time to at least take a look at all of this since this material was published a week leading up to the hackathon. So if there are questions on this last portion, please feel free to ask. If not, we will move on to application to Haskell. Okay, so now to Haskell. So all of these notions that we just went through, sets and functions, are strictly applied to Haskell. I'm gonna take the risk here to say that sets in Haskell are equivalent to types in Haskell. Same for functions in math, the same concept as function in Haskell. But I want to warn you that there's a tiny bit of a difference. And as you get more into this, we will talk about it. I will advance with this, we will talk about it. But for now, it's fairly true to say that sets in functions translate into types in Haskell, and elements of sets in function translate into values in Haskell, because every value in Haskell has a type. So the type is the set, it's like the container, and then the value is like the cake that you make out of like the cake maker or the container. Yeah. So functions in mathematics, the properties and the characteristic of function in mathematics are the same characteristics you have in Haskell. And as a starting point, we can, run through a quick overview of Haskell. So everything in Haskell is an expression. An expression can be values, functions, or declaration. Functions are a special type of expressions. I think I'm repeating myself here. And value or result of expression evaluation. So when I have an expression, let's say 2 plus 3, for example, I can evaluate that expression to return a result that will be 5. If I have a function, I can evaluate that function, the function that takes a parameter, I can evaluate that function to obtain a result. Next characteristic of Haskell is it's purely functional. Again, every function in Haskell is a function in a mathematical sense. It's pure. Meaning what? When you call that function or you execute a function, you are actually, if you execute a function with, let's say, some value, now and come back 5 minutes later and execute that function with that same value, you get the same result. It gets us to the quote, which says, the same causes produce the same effects. And this is really a very important concept in functional programming. There's not too many moving parts, variable mutating and changing without you having control. You actually have control when you work with functions. So functions can only work with their input, meaning if you don't get the result you return depends on the input. And I will digress a little bit over here and show you that, for example, here, when we define this function, g of x, you can see that this result over here only depends on this x. It's not going to grab any other variable somewhere to return. It only depends on what you gave it as an input. So let's go back to the fact that function can only work with the input. So when you're at home and you're using your machine to grind, let's say, I don't know, peanuts. Well, what you get on the other end is not gonna be anything, it's not gonna consist of anything you didn't put in the head of the machine. So you're only gonna get what you put out, your strand that you're using, the peanuts, and then on the other side, you will get crushed peanuts. So that's how functions are. So look at the function as a black box. Haskell is statically typed. What this means is every expression, every value in Haskell has a type. Meaning you can have value in Haskell that don't have types. If you declare a value in Haskell without providing it with a type, and then the compiler will suggest a type. At this point, it will offer you the biggest container, meaning the biggest type possible that you can fit your value within. So, which leads to type inference, which is means that Haskell can automatically derive, your type for you. So Haskell is concurrent and parallel, meaning that, it's really the fact that you can mutate variable in Haskell, it uses functions and all of that makes it really nice, a nice candidate for concurrent and parallel software or programs, meaning software that can run in parallel and concurrently in different machines or using different processors within the same machine. Okay, now types in Haskell. What are types? Again, relate to the concept of sets in mathematics. We already said that. Haskell with types, you get readability because everything is a type. So it's just like a Lego of types when I'm writing my functions and putting my functions together to do more work for me. I get safety because I know the type of everything. So if a type doesn't match, the compiler will complain at me. And finally, types are a great tool, to group and classify concepts. I can create a type for person. I can create a type for, let's say, a car. It depends on the program that I'm writing. But I can create types to represent a concept. I can create a type for a student. Let's say his grade and his with his name, for example. I can do that in Haskell. So in Haskell, the way you define type is using this anatomy, where you have the type, the keyword data, and then over here you have the type, something called type constructor, which is the name of the type, and then here you have the value or data constructor, which is so here you are specifying, like, let's say, the name of the set. And here you are telling the property on how your set could be constructed. If you remember, we need to always go back to this notion of sets. That's how you define new types in Haskell, new data types. Another way to define new data types is to use the keyword type. And here, it's the same thing. You give the name of the type. And here you tell Haskell how you construct those types. What's the difference between data and type is that type is used to create synonym. Like, in most programming, people use strings for names and let's say first name, last names. Well, in Haskell, you can actually create a variable called name, which is synonym to string. But they are two different things, even if they are synonyms. New type is a way to create like a wrapper around types, and we will see that. So it's another way of creating types. So we just talk about part one being the data constructor, the type constructor, which is also the name of the type, and part two being the data or value constructors. We will see some examples. So as an example, Haskell comes with pre-built types, one of which is bool. And bool, which stands for Boolean, has two possible values. So if you remember, we'll look at this. We have our data keyword, we have bool, and then we have bool, which is the name of the type, Boolean, and then we have over here the data constructor. So I can either create a bool which value is false, or a bool which value is true. So the syntax for declaring a value in Haskell is as follows. So we have this, where we give the name to our value. I can say, is the hackathon happening right now? I set it to true, it's true. And now I can ask the type of this, and the compiler will answer that it's a bool. So you use this command within Haskell to ask the type of a value. So we define the value there. We ask its type over here, and we get this. It's a bool. So I think it would be good to just get to the practice. Give me 1 second. Clear. So over here, we will come back to it on how to set you up probably tomorrow, so that you can also have your coding space like this online. It's REPL. But what we are interested in is defining a value in Haskell. So we called it is the Haskell. Can you guys read? Oh, let me do this. Get a little bit bigger. So that's the name of my value, and I do equal true. And I hit enter, and now I want to question Haskell about the type of my value. Let me do this. Clear. So I'm gonna restart. So we define the value, and then we are asking Haskell, what is the type? Bear with me. What is the type of the value I just defined? And you see here we obtain bool, like that. So, so here we are learning about this command, the column and type, or another way is just to write here column T, like that, and that will do the same job. So in Haskell, we, again, to define a value, we could do, for example, x equal to, like that, and then we can ask the type of x, like that, and we get this strange thing that we will come back to. Don't worry about it. But since we know about Boolean, which is a data type that allows us to tell whether something is true or false, we can, for example, ask, Haskell, whether x, we know x, we define x equal to, and we can ask Haskell, x minus 2, is it equal to x divided by 2? So obviously the answer is false because our x is 2, so 2 minus 2 is 0 on the one hand of the equality sign, and x divided by 2 is 1. So we have 0 here and 1 here, and we are comparing. This is the comparison operator. We're comparing 0 and 1, and we get false. So that's how the data type bool that we just saw is used. To finish this practice session, if we want to find more about the data type bool, we can simply type info and the type name bool, and here we get a bunch of things. But what's interesting here is you see how it's defined, using the data keyword, the name of the type, and the value on how you construct it. So I think I'm gonna stop there, and we're gonna continue with another type, built-in type. And please feel free to ask a question if you have any. Okay, so we'll continue. So and then we have the next type, which is Char, which stands for character. And this is the type that is used in Haskell to represent, all characters. And that's how it's defined. It's a little bit tricky, but just know that it's referring to all the possible characters, both alphabetical and numerical, that you could have out there. So one example would be his first name character is, and I defined a value, the character F. You use single quotes like that to define a character, and I could also define another value. His name's last character is N, so both capital, lowercase, and even a number. So as long as you have it within like single quotes, you can put digit as characters. And just to try this very quick, I will copy these two. And let's switch the screen. I will clear that up. And so at this point, if I hit enter, oh, by the way, this is called the repo. And again, we'll come back to it tomorrow. So I just defined a value called his name first character is, I gave it that, I just defined a variable and I gave it that value. So that one, so if I want to display my variable, I can just write its name and then hit enter. As you can see, Haskell will display the variable. If I write this one, and then I hit enter, I'm getting ended. And if we go back here, and if we want to reuse the bold data type that we just talked about a few minutes ago, we can ask ourselves if those two characters are equal by doing something like this. First character, is it equal to his last, no, his name, bear with me. So and here we are going to get obviously false because these two characters are different. So let me switch back to this. So we just talked about the bold data type and the character data type in Haskell, and we also saw how we can define values of that type. Now we're going to move on to numbers. So numbers in Haskell come in two groups. So there are two big categories for numbers. And if you remember, if we ask Haskell, for example, if we define, let's say, a variable called number of participants, let's say of this hackathon, and we say 30, and I think we went over that number, that's great. And if we have, let's say this, we define this and we use that column T to, figure out the type of this, we get this right in here, which is a little bit like alarming because you would expect something like int and so on. But actually Haskell groups numerical value into two big parts, which are integral, that could be int and integer, and fractional. Fractional meaning anything that has like a decimal point value. So float, double, rational, and scientific. So integral holds int, which is a set which has a minimum and maximum value, and integers is for representing arbitrarily large or small numbers. So it doesn't have a limit like int. So the point here is that when we talk about numbers, Haskell has this, what I would call a mother type, num, which then holds like this integral and fractional as sub groups. And so when we come here and we tell Haskell that we have a number of participants, which is 30, Haskell doesn't know what to do. He's like, oh, look, 30 could be an int, it could be an integer, it could be a float, it could be a double. But since you didn't specify, I will give it a type. And remember, we talk about type inference in Haskell. So Haskell will always try to give it the biggest type possible. In this case, num, saying it's a numeric value. That's what it means. And this is also called type class. We'll get to that hopefully at some point. So let's go back to number and do a little bit of practice here. So allow me to share my REPL. So I'm going to clear my screen, and we're going to define a variable called number of participants equal, let's say 30. And remember, by doing like this, if we ask for the type of number of participant, I forgot something here, my T, number of participants, Haskell would tell me that it's a num because it doesn't know what to do. If I want to be more specific, when I define this type, I need to tell Haskell which specific types I want to use. So the way you do it is you introduce this semicolon, a column, and then you specify a type, int, for example. There you go. So at this point, if I go back and try to figure out the type of number of participant, and then Haskell will tell me it's actually an int, you know. So if you leave it alone to Haskell to figure it out, he put it in the biggest container possible. If you want to be specific on what you are defining, the type, you see, this is like my set. This is an element of the set. 30 is an element of this set int. Then you specify like that, and Haskell will not use a type inference to figure out like the type for that. So now we also talk about float as a way to represent decimal numbers. Let me clear this up. So if I do average, for example, equal, what would I do here? 1 divided by 3. And I ask Haskell about the type average. You see, again, Haskell will give me a fractional because 1 divided by 3, yes, it has a decimal, but it could be a float, it could be a double, it could be, you know, any other type that has like a decimal part. So if I want to be specific when I define that, I will tell Haskell to, I will tell Haskell specifically about the type by using this writing here and telling it, for example, float. And at that point, if I query the type of average, you see we are getting float now. So, and then a quick note, float is for representing decimal value with single point precision. So which means like fewer numbers after the decimal point. And double is for presenting like values with double decimal values with double point precision, which means with a bigger decimal part. So if you're working with numbers in which decimal parts really counts, you want to keep that decimal part. You don't want to cut it off as it happens with float. So are there any questions? Okay, so we'll proceed. So again, I would invite you to search about rational and scientific. These are, very nice types that we have in Haskell to work in the scientific field. So now let's move on to some operations on numbers. So obviously we have addition, we have multiplication, division, subtraction, and modulo, which is kind of an interesting one. So addition, as you say, if you see, if you enter that in your REPL and hit enter, it evaluates, it adds two numbers. The other way of writing addition is in prefix notation, meaning that you state the operator first and then you provide the operands, and you will get the same number. So subtraction, so 5 minus 3, you get 2. And then you can do, the same thing with minus. You specify the operator first, because actually operator in Haskell are functions. So, it's like a functions that takes 2 parameters. So that would be 5 minus 2, 2. So, and here you can see the type of the addition that returns that strange type. And remember, num is just saying that it's a numeric value. So A is a type that is a numeric value, and here it could be an int, a float, all those numeric type we just talked about. So now we have comparison operator that allows you to compare things of the same nature. So inferior or equal, and so on. Equality, we already saw that when we were comparing, two values. And this is how you would use it. So you would question Haskell, 2, is it inferior to 5 or equal to 5? Yes. Is 2 superior to 5? False. And is 2 inferior or equal to 2? Then that would be yes, because it's inferior or equal, it's equal. So I know I already constant and polymorphism. So when we talked about Haskell putting stuff in the biggest container, we had an expression like this where we define a value, and then we try to figure out its type, and we realized that we had this strange thing with a P there, and P, and P here. So what it's saying here is that this P is constrained by this type, which is fractional. So P has to be a fractional, meaning, either float, double, scientific, or rational. But then we know that types in Haskell usually always the names start with capital letters. But since this is a one that starts with lowercase, it's a way to express polymorphism, meaning like this time polymorphism, meaning that it can take multiple forms or types. So this is something actually that we can turn into ints or floats or doubles. That brings us to the notion of type variables, which in fact are, like type variables are actually, polymorphic in the sense that when we have, for example, let's say a list of things that we want to work on, and this is the Haskell notation for a list, we have some functions like get me the first element from the list, which is called head. And here, the function doesn't care about like the type of the element. It knows how to get the first element. That first element could be of type integer. It could be of type anything, Boolean or anything. And that's what we call type variable. We also have the function length in Haskell that would get a list of item. Look at this as a list, a T, a list of items of type A, and return an int, which is the length. There's an error there. Ignore this case. And return an int, which is represent the size, on the count of the elements within the list. And this function here, you can see we have a there, which is a type. It could be a list of int, a list of people, a list of anything. So that's called a type variable. So variable that's whose types actually change. So or vary, if I can put it that way. So now we move on to, and I know we're going super fast. Tomorrow we'll get a chance to come back to this through exercises. We get to list, the mathematical construct here would be that list can be subsets of like a set. We talk about like subsets. So lists are actually used to contain multiple values that have the same type. So they have to be homogeneous. So I can have a list of int, a list of floats, a list of characters, or a list of booleans. But in no way I can have a list of int and characters or a list of bool, and no, it has to be homogeneous. And this is how it's constructed. It's defined. For now, just for learning, purposes. When we advance, we'll get into this in more detail. So in Haskell, the way you actually declare a list value is you do this. So let's say at the end of this hackathon, we have, when we run the challenge on Saturday, we have great grades. I can only see 20s and 18s there, which is great. And, as I'm defining this, I'm specifying the type there. I'm saying that, it's a list, these braces, introduce list, whose elements have type float. And as you can see, here I've constructed my list, and that's the variable that I'm associating with this list. So, of course, we can figure out a type, and then we get that it's a list of float. And if we define this without specifying the type, Haskell will do its magic of type inference and tell us it's a fractional because it realized that it has decimal parts, and it's a list of A's. A's could be, it's a type variable within the fractional type class. So next, other questions at this point? Cool. So we proceed. Next, we'll move on to strings. Strings are actually an interesting type in Haskell because a string, which is a list, it's actually just a list of characters. So an example of string would be anybody's names here. It's a string, and it's a list of characters. So the way string is defined as a synonym. And remember when we're talking about like the keywords that we use in Haskell to define types, we mentioned this type. So string is actually a synonym of a list of characters. Okay. So by typing info string in the REPL, you will get this, and you can see the definition there. And here we can define different greetings in different languages. In the US, we say, "How are you doing?" That's a string. You see there a list of characters. And here to define a list of characters or a string, you have to use double quote, not to be confused with single quote when you want to define one character. Okay, so here in Kikongo, which is a ancestral Congo language, to say good morning, you say Mbote Nzolapangi, which is actually meaning like the meaning is like receive the sacred fire that will allow you to heal, and it's a little bit complicated. We'll get to it, but it's quite interesting. You should double check and do some research on it. So that's the type string in Haskell. We can talk about some functions on list. Head is to illustrate that. I will just show this, this picture capture. So we have here, imagine we have a list of items. So each of these part of the body of a millipede represents an element in the list. So the head of the list is the first element in the list. So the function head will take a list of things as input, and it will return the first element in the list. The function tail will take a list and return all the elements except it return another list containing all the elements except for the first element. Init will do the opposite pretty much of tail. It will take a list of elements. It will return all the elements except for the last. And the function last, when given a list as an input, will return only the last element in the list. And over here, we have many other functions. Null will return true or false, respectively. If the list has 0 elements, no elements, is empty, or the list has elements. Lms will return, lms takes a list and an element and will tell you whether that element belongs to the list or not, and so on. Take and drop, we will come back to them tomorrow. But here's an interesting one. Reverse will take the list and reverse the order. So the first element becomes the last, and the last element becomes the first, and vice versa for the following. Concat combine two lists into a bigger list, and plus plus does the same as concat. So here we get to list comprehension, and remember when we talk about when we saw set, we talk about sets. We mentioned that you can define a set either in extension, where you specify all the elements, or in comprehension, when you just give the properties that all the elements are verified. So here, for example, this is how we write something in math. We say like the set S is all the elements. This is the output of the set 2 times x, 2 times x, in such a way that x belongs to n, and x is comprised between 0 and 10, or inferior to 10. So this is basically, the same set we defined in the math session. So we call this the predicate. X is smaller than 10. It's the predicate. And in Haskell, this writing will simply translate into this. So we have x times 2. So we have the list bracket opening and closing. And then we have x times 2, which is what the exit of, the output of our function. This is like a function. And then we have our predicate. We say, tell them just grab all the elements from this interval. So from 1 through 10. And when x is set to 1, we'll get 2 times 1, that's 2. When x is set to 2, we'll get 2 times 2, that's 4, and so on till 10. So here, one example of set comprehension could be that we have these two sets, all Cantos. Cantos are women in Kikongo. So we have Mercy, Emilia, Ahura, and all Bakala, Sydney, Josh, and Paul. So we have the list of women, the list of men, and we are trying to build like challenge group. So we can use list comprehension in Haskell as we define. So the result is going to be couples of Canto, a man and a woman. Women first. Women have the priority in our context. A woman and then a man. But how do we construct this? So it's as if I'm saying this is what I want to construct, and this is how I want to construct it. So every Canto from here, women, will be drawn out of all Cantos, meaning from this list here. And every man that I specify here will be drawn out of this list here. So that's how we can use this comprehension to, do interesting stuff. And in addition to this, I can add a condition over here and say that I don't want the man called Paul. I'm sorry about that, Paul. And when I do this predicate that, this thing here cannot be as value Paul, so it will ignore Paul in doing like building these couples, this group work. So next, the next data structure is tuple, tuple, and this is how it's defined. It's actually a way to hold like, values that are heterogeneous. So we talked about list being a way to hold things that are the same type, but with tuples, you can hold things that are different types. So again, here you can see how we are defining, a list, a tuple with a string there, a list of character. Here we have a number, and then we have another string. So, they're actually useful to hold like things that are representing the concept and the context, but that have different meaning. Like we could be interested in representing, let's say, the grade, students and the grades, and we can build tuples, which first element is the name of the student, and the second one, for example, is the grade in which he belongs. So, this is available to you. You can go and try it by yourself just by copying all of this and pasting in your repo, but we'll come back to it tomorrow. Wow, that was all about types. Now we're gonna run through functions if there are no questions on types. Great, so functions in Haskell. So functions are declaration and definition. Declaration is about specifying the type of the function, and definition is actually providing the body of the function. So like we mentioned, function takes inputs and they return outputs. And the analogy that I took when we were talking about function in mathematics is you have a grinder, you have your peanuts, you mix it with like some condiments, you want to make dole sauce, and you can look at the machine or the grinding machine as your function. That will be this box here, which knows how to grind. And as input, we can have different inputs, which are peanuts, our condiments, tomatoes, and so on, garlic. And then we also have the electrical input, which is another input to the machine. And then in output, you will only get things that are made using all the input that you have put into the system. This is very central to Haskell, the notion of functions, because what happens in other programming languages is you get to work with methods that can, return this output or do machinery in here using stuff that are external to the input you provided here, that are subject to change. And that makes it really hard in the sense that you can call this function with this input at this time, and then in the next second you call it with other input, the same input, and the result, the outputs here are different. So in Haskell, we have functions in the pure sense, and that makes it really cool for developers. So again, functions declaration consists of the name. We give the name to the function. And that name has to be lowercase, so lowercase, okay? And a function comes with its type. So in order to define a function, I will give it a type first. And on this left hand here, we have what we call constraints, and we'll come back to it later. But on the right hand over there, after this symbol, we have the list of the inputs, separated by that arrow. So input type 1, so we specify the type of the input like that. And then we have one output, and we specify its type. Now, when we are defining the body of our function, we state its name again. Each input that we had here corresponds to one argument here. Each input corresponds to one argument. And then we have the equal signs, and over here we have the function body, which actually works with this argument to return a result. So that's the anatomy of defining a function in Haskell. Are there any questions on this notion of function? Great, so we'll progress. So creating a function. So again, in order to create a function in Haskell, let's do it by one example. So what we're gonna do, add square. So I will switch to here. So I will introduce you to a new construct, which is, well, we don't have to, but as of now, so add square, what was it? Add squares, I think, is a function. So that's the name of my function. And what I'm going to do here is I'm going to provide it a type. So I'm going to give it a type before I actually define my function. So I will say that my function takes an integer as its parameter. I have my arrow, another integer. So I will compute these two integers to return another integer. So obviously I get an error there because I can write that in the REPL directly. So what we're going to do, it's going to give us a chance to introduce you to a code source. So in Haskell, a Haskell source code file has that extension. So it's main, I call my file main.hs. And, within this file, I can write my code. So there's already some code in there, which is we will come back to that, but ignore that for now. So I can define my function in here. So that's my function, and I gave it that type. Remember, this is to specify the type, that column. And down here, I'm going to provide a definition for my function. So now we can see here that my function has two parameters, so I need to name them. So I will call it n1 for number 1 and n2 for number 2. And I need to return a result, which is an int. But now I need to use this 2. And I think what we had here was that we will return like the square of x added to the square of the second y. So what we'll do is n1 n square plus n2 square. So now we have this function in the file, but how do we access this function here in my repo? How do we execute it in here? So first of all, we're gonna clear this up. So my file, I need to load it, and the Haskell command to do that is load. And I type the file name like that, and it compiles. If you remember, we talked about what compilation was in the first part of this hackathon. And at this point, I can start typing the name of my function and hit tab to complete or to complete. And let me just make some space here so that you can see to autocomplete. And now my function I know takes like 2 int, so separated with space. That's how you pass in parameters, 2 and 3. So what I expect is 4 plus 9, and that would be 13, I think. There you go. So I get 13 by hitting enter. And also something we could do is check the type of add square. And oh, sorry, I had 2 T's here. I get rid of that one. And as you can see, my function has typed exactly what I specified. So that's how you create a simple function in Haskell. So again, you have a file that you create with a capital letter. You have a dot extension HS, and then you can define your function, both its type and its definition. And then you load it into your repo over here. You load it using the command load, column load, and specifying the file name after that. And then you can have access to your function. So let's move on to our next point. Are there any questions? Okay, so again, we already seen that. We already seen how to call the function. And now we will move on to conditional expression. So in Haskell, we have some construct that we can use to create even more interesting functions. One of them being like if then else, which basically does what it sounds like. So it will check the condition that we put here, and if that condition evaluates to true, it will then return this as a result. But if the condition we specify here, evaluates to false, and then it will return that other expression that we have there. One example would be that, let's say we define a variable for, and then we want to define another variable x, and we want to use the value of 4. So we're saying that this will evaluate in either 0 or 1, depending on what this expression returns. So mod is a function that takes 2 integers or int and return true if no, actually I think there's a mistake there. It returns 0 if the first one is divisible by the second one. So in our case, we have, for example, 10 here. 10 is divisible by 5, so it will return 0. And it will return the rest of the division if it's not divisible by 5. So let's say we had 11 here. 11 divided by 5 would be 2, and we have a remainder, which is 1. So this function here will return 1. So what we want to do actually here is compare this to 0. So if modulo of of A, whose value is 4, is equal to 0, then return 0 or 1. So X will either get 0 or 1. In this specific case, 4 modulo 1 is what? The rest of the division is not 0. So it will set the value of X to 1. So you can run that as an example at home, correcting the mistake that we just highlighted here. So Wada expression. Wada expression allows you to define functions in this way. You define the type, and then as you define your function, you can omit the equal sign that is here, and then you have your Wada here. What comes after the Wada is an expression that evaluates to true or false. So, and if this condition is met, whatever you write on this right side will be executed or evaluated. If this condition is not met, the next Wada will evaluate. Otherwise, means for any other configuration, they will then evaluate to whatever you specify here. So here, for example, we are trying to figure out the maximum number of A and B, and as you can see, there's a mistake there. Obviously, our function is taking 2 parameters and returning the biggest. So there should be another error there with an int. So we say that if A is superior to B, then A is the maximum. Otherwise, B is the maximum. So that's how you use Wada. We'll come back to this in more detail tomorrow. So the let in is actually what you use in Haskell to bind variable to values, and and the syntax is that you use let to introduce a new variable like that. On the left side of the equal, you give it a name. On the right side, you give it the actual value. That's let in. And we'll come back to it tomorrow. So the case expression, as its name says, you have a pattern, so you have some sort of variable or value, and you're questioning its format or its pattern. XS here stands for a list, and I'm wondering if this list is empty. If it's empty, I will return that. If it has exactly 1 element, I will return that. If it's anything else, it has at least 1 element with another series of elements that could be empty, and then I will do that. So this is a case pattern. Again, we will come back to that. So the where construct in Haskell allows you to be more declarative. It's, for example, we have a function here that calculates the total area of a cylinder. We know that the total area of a cylinder, by its definition, it's the side area, plus 2 times the top area. Think about your glass that you drink water in. You're trying to figure out like its area, the top part and the bottom part. That's what I call top area here. And the side area is like the lateral area when you have I actually have my glass of water here. So that would be the side area. And here, the top and the bottom would be the top area, which is same as the bottom area if we have like a perfect cylinder. So in this case, so I'm stating my formula without knowing the values of this, and I'm using the where keyword here to then say side area equals this and top area equals that. So where allows you to introduce express a declaration and express yourself in a more declarative way. So pattern matching. Pattern matching actually allows you to match the body of your functions to different patterns. Like if, for example, we know that the bool type can only have two values, it can either be true or false. Now, if I want to write a function that takes a bool value and negate it, what I would do, I would just, state all the possible case, with the body of my function. My function can be, with either a true or a false. And in there, I would just negate that value. So same here. So if I have a function that takes numbers from 1 to an infinite number, and it returns, the number in letters, but I'm mostly interested in numbers from 1 to 3. So what I would do is I would match. I would say, if you give me this, you call this function with 1, I will return you 1. If you call it with 2, I'll return you 2, and so on. So this allow us to avoid using if and else, if and else within if and else, and which can get pretty messy when we start like having like so many. And this writing here is just saying that not, anything else, just return that. So in Haskell, you just write underscore to do anything else when you're pattern matching like this. So anything else other than 1, 2, 3, just tell me that it's not between 1 and 3. Other questions before we move on to the last section? Okay, so now we come to what we call higher order functions. So in Haskell, functions are first class, just like in object-oriented in Java, object of first class citizen. What that means is that functions can be, I can declare my values and assign. So functions can do pretty much, you can do with functions everything you do with values. Let's put it this way. So like we talked about list of things, for example, list of value, list of integers. I can have a list of functions in Haskell. I can have, let's say, a type that has a person, that has a function within its list of argument, list of attributes, that has a function within its list of attributes. That's what I meant to say. So in Haskell, functions are first class citizen. Now, a higher order function is actually a function that takes another function as input and return either values or another function. So we will see some example on this, but let's move on first. And carried functions are actually this concept that you can have a function with multiple values, but when it comes to execute those functions, you don't provide all the values to the function. So you call your function, giving it, let's say, one value, one parameter out of like 10 parameters or 3 parameters that the function has. So what will happen is Haskell, that evaluation, we return another function but with fewer inputs. So that's the concept of carry. So I could be within my code, I have like a function that takes in, let's say 2 parameters. And from that, I can create another function just by applying 1 parameter to that the first function and obtaining another function. So that's the notion of carry function. So as an example, in Haskell, you have the map function. When you query its type, this is what you get. And as you can see, these parentheses around like parameters, input parameters, is telling you that this is a function. So the map function takes as input a function, then a list of items of type A, and returns a list of items of type B. So as an example, before we get to the example, let's do filter. Filter is another higher order function because it takes as input a function and it returns, it takes as input a function and a list of things, and it returns, a list of things. Remember, the last thing is the return type, and all of this on the left before the last, parameter are the input types. So now to do something interesting to explain this and probably wrap up with this is we can define, let's do this. So we go here and we define a function that we call double grade. So that's its type. And then what the function does is it takes an input, a grade, and it doubles it, as simple as that. So now what we can do with this function is we can define, let's say we define this, participants. So participants grade, we can assume that that's the list of grade that we got after our hackathon challenge. And we are interested in doubling all the grades, all these grades within that list. So remember, we talked about map. So what I'm going to do here is I'm going to come over here. I'm going to clear my screen. So I'm going to reload. And this time we're going to do column R to reload the main file, the source code file, to include our new code. And then we'll question the type of double. So our function is in, and we can also type participant. So we have the list of our participant grades. And what we can do here is we can say double equals. So since map is a function that takes a function in input as an input, so we can do map, that's a function, and we pass it our double grade function as its first parameter. And then the second parameter, we pass it the list of all the participants here. We can pass it explicitly like this. And when we hit enter, double, bear with me. So if we try to display double, you see what happens is, map as a higher order function took in a function and a list of things, and it went down to apply this function to each of these things in the list, doubling its value as the function indicates over here. So that's to summarize here, map as a higher order function. What it does, it takes in a function, a list of things, and return a new list, having applied, that function on each element on the list. So another higher function that we have is filter. And as you can see, it takes a function that takes a predicate, function that takes in one element and return a ball are called predicate. So we could be interested in filtering, for example, a list and finding out and just retaining people that have a grade that meet a certain condition. So at that point, we'll define that condition through this function and then use the filter to, filter out those items. So I will just copy one example that I have here since we are running out of time. Excuse me. So do this. So over here, let me remove that. Sorry about that. So we define a function called is divisible by 2. That takes an integer and return true if that integer that it took is divisible by 2, or return false if not. So the way we would implement it is just saying that get that number, integer, do modulo of that number with 2, and we already know what modulo does. If it's divisible by 2, it will return 0. So then when I compare to 0, 0 equals 0, I'll get true. If not, it will return the rest of the division of n by 0. So, and that will be different from 0, and it will return false. So now we'll define these numbers, and we will use filter, pass it this function, and then pass it this list, and it will filter out everything that is divisible by 2. So if we come here, practice land, before we will reload for our new code to be taken into consideration, and we do filter. Bear with me, filter. First argument parameter to filter is divisible by 2. Let me just clear this up. So again, we do filter is divisible by 2. That's the function. So we actually passing a function as a parameter to our filter function. And now the second argument would be our list. So we could do 1, 2, 3. And what we expect here is a new list having 2. So that's what we get. So that new list with 2, because within this only 2 is divisible by 2. Okay, so very quick as we are wrapping up. Let me bring this back over here. So that was about higher order function, function composition. We saw this notion in math, where we have this writing. This is a very core and important concept in Haskell, in the sense that, you write little functions that do little work, and then you can combine them into bigger functions, and using a composition, for example. One example could be that we have a function that knows how to multiply by 2. And then we have a function that knows how to take something and add 5 to it. And now we want a function that knows how to do both. So in that case, you use function composition. And remember, the return type of the inside function has to match the input type of the outside function. So in this case, for example, whatever f takes as an input has to be the same type that gx returns as an output. So we'll come back to this notion tomorrow, and we spend some great time, looking at it through exercises. But yeah, parameterized function, which is the last point here, is also the same concept as we mentioned. So imagine you are in a situation where you need to, define greetings. You have you need to define greetings, a parameterized greeting function, and what it does, and it takes a language and it returns a function that knows how to say hi in that specific language. So you would do that through parameterized functions, and the way it works is that we will define a function, as you can see here, that can take in one parameter and its return type is a function. And remember, we talked about currying, where you can have function with multiple parameters and pass it the first parameter and it returns a function. So tomorrow we will come back to this as as an example. I think we are really running out of time, and I don't want to exaggerate. But yeah, so as an activity, you can go ahead and try to do this and try to make sense of all of this here. But tomorrow we will come back and do some practice exercise to make sure we are really getting these notions. With that, I will end and probably return back the control to Megan.
Hi, everyone. So we know we went a little bit over today. I think we also started a little bit late. So thanks for sticking around. I think I got the attendance all sorted. So thank you for those of you who stayed till the end. If anyone has any questions, feel free to unmute, or if you want to just say hi, feel free. Also, no pressure. I know you're probably like feeling all overwhelmed with math right now. But we'll be very happy to see everyone again tomorrow, again for practice exercises, and then on Saturday for the actual challenge, hackathon challenge.
All right, sure. We are looking forward to it.
Yeah, thank you for having us.
Oh, absolutely. Thank you too for being here.
Yeah, thanks for coming. I'm gonna hop into the French room.
Well, I guess yes, go ahead.
Yeah, thank you very much.
Absolutely, my pleasure.
Okay.
So again, please, if you haven't done it yet, try to create an account on REPL 8. That will save us some minutes because it will all be about practice tomorrow, and we'll share like the same coding space so that we can have you coding as well.
Also, what's that about?
Are you talking?
Okay.
Yeah, so I think we're good. And again, thank you very much for showing up. We look forward to having you tomorrow.
Bye.
Bye, bye. Have a good one, guys.
Okay, bye-bye.
Bye.
Where you at?